talking about Vegas, which is definitely a favourite subject of mine. What we're going to look at today is the last day that we're going to be doing confidence intervals on proportions. And hopefully we've done them to the point where you can do them upside down, swinging from a tree, right? You've seen every permutation. But we're going to do one more day. And we're going to be looking at the difference in two proportions. And basically, I've just got a summary of all the kind of information and things that we will be using today. We did a kind of interesting one at the end of yesterday when we looked at COVID data. And a couple of the questions I've got right now are actually real data as well, which I like. Essentially, if you are looking at the difference in two independent proportions, then the confidence interval is generated by this formula here. The Z star is the magic Z score, and it depends on what kind of confidence interval you're looking for. So if you're going to do a 99% confidence interval, it's this number. On the other hand, if you do a 95% confidence interval, it will be this number. And what you'll get from this is an interval that represents the difference between the two. So it's not a confidence interval of either of them separately, it's actually the difference between them. So three things are going to happen, typically. You're going to get an answer that looks something like this. And I'm picking nice round numbers. You could get that guy. You could get that guy. Or you could get that guy. That's the kind of intervals that you've got. Now, me personally, I like percentages, but that's fine. In each one of these cases, we are looking at the estimate for the difference in the two proportions. And let's say that they're all 99% confidence intervals for argument's sake. If you get an interval and they're all negative, that is significant, right? That means something that we can kind of bet our house on. And what that is saying is essentially that there is a difference, a statistical difference that's provable, right? So it's statistically significant difference. Not only does it tell me a difference, doesn't it tell me who's the big guy and who's the little guy? And because they're all negative, doesn't that make P1 smaller than P2? So we could say that this is a statistically significant difference with P1 definitely smaller than P2. And if you wanted to be nitpicky about it, isn't it definitely smaller by at least 10%? Right, could be as high as 30%, but definitely 10%. Now, this one here is also statistically significant. And the difference here are all positives, right? And in this case, not only can we say that there is definitely a difference between the two, can't we say that P1 is bigger than P2? Right? Since the difference is positive, the first one has to be bigger than the second. And I could be saying that not only is P1 bigger than P2, couldn't I also say it's about at least 10% bigger? Right? So we can actually put a number on the bigger. And then you get this guy, and this guy contains 0. So if your interval contains the number 0, then it's not significant. That means we have not found any evidence that there's any discernible difference between the two populations. Right? They could be the same, they might not be, but we haven't been able to find one way or the other any significant, statistically significant evidence to prove it. And let me pick one of my first questions in. Which one should I pick? Okay, here is a study that was conducted on policemen. and they were looking at the health of them. And they collected data, and this study reported that in certain states, retired male policemen were more likely to have heart attack disease or heart disease than equivalent men of the same age. Right, so you found a retired policeman at 65, right? And you got that group, right? Maybe it's 60 to 70, that's more likely, right? And then you get retired firemen or retired doctors or retired taxi drivers, right? And you looked at them and you compared them. And in this particular set of data, we had for the police a sample size of 250, of which 34% had some heart issues. And then the second one, they're just calling them non-police, so it's a combination of all sorts of people. And the second sample was a larger sample of 850. And the percentage of them that had some kind of heart issue was lower, which is 16%. Okay. So far, so good, right? And they're going to ask some questions from other topics. So here's the first question. Based on what I told you here, they give you a list of what kind of, how's this information collected? Isn't this an observational study? Right. They didn't split them into groups and give a placebo and do all sorts of things. It wasn't an experiment. It wasn't anything that was controlled. It was just, we found some, randomly found some policemen and found out what percentage. And it says here, do you think, just looking at this data, so right now, it's just your gut feeling. Do you think that percentage difference is going to be significant? Do you think the difference is big enough that it's probably going to survive statistically? I would agree. If you were trying to quantify it, aren't they pretty decent size samples? And isn't this difference pretty massive? That's vague terms, but you get what I mean. Now, if this was 34 and this was 33%, wouldn't I be not really confident that there was any obvious difference? Or if this was 25 and this was 30 people, right? Very small samples, then even with a large difference, it might not be, that significant. Because if you've got a small sample, doesn't it only take 3 or 4 people more with a heart disease for the percentage to increase by a lot? It doesn't take too many. And so that would be the answer to their part B, and they give you some pictures. And then we get to the question, well, we're going to do a difference between them. So that means we're going to use this fella. So I have a whole load of stuff up here. I wrote that one down. And then after I wrote that one down, I realized that I should have probably wrote that one down. But you know that they're both the same, right? And you notice that from time to time I forget and I write this. So if you're wondering why there's 2, it's just because after I wrote that one, I realized I could have done a smaller version. So let's put this package together. I can find out Q1 heart, it's the other 66%. And I can find Q2 heart, it's the other 84%. I'm going to do a 95% confidence interval for the difference, and we'll see where this goes. P1 heart, take away P2 heart is 0.34, take away 0.16, and that comes out to be 0.218. 0.8. That's all right. The standard error for the difference between them is the square root. I'll do the P1 Q1 version. And I'm looking at 34 with a 66 divided by a sample size of 250, added to a 16 multiplied by 84 out of 850. And so I now have that guy. And it goes. Square root of 0.34 times 0.66 divided by 250, add 16 times 84 divided by 850. And do they mention any accuracy here? 3 decimal places, okay. So the answer is going to be 0.032 to 3 decimal places. I need the magic guy, and this fella is going to be 1.96. So I should be able to put this package together and find my 95% confidence interval. So it's P1 hat, take away P2, give or take the magic Z score for 95, followed by a square root. Why am I doing that? P1 hat, take away P2 hat, plus or minus magic Z score, standard error. I don't need to write the formula down again, I've got it up there. The difference we got was 18. It's 1.96. And the standard error is 0.032. So I'm looking at this fella, and 1.96 times 0.032 is 0.063 to 3 decimal places. So it looks like my interval is going to be 0.117, and it could be as high as 0.243. For me, that's 11.7% to 24.3%. So the difference between policeman's heart rate illness and non-policeman heart rate incidents among older retired people, there's a difference, it's positive. So statistically significant that retired policemen have a higher incidence of heart rate than other professions. And then you could maybe look into that in detail if that was your thing, if you wanted to do. I could imagine someone in the, I'm trying to think what that would be. It's a borderline. It could be in the medical side, it could be in the social science side. But I could imagine you could do a PhD where you would actually go into the details of that. And you might come up with some suggestions. I'll pretend I know what the heck I'm talking about. Maybe you find out that policemen, when they retire, aren't looking after themselves maybe as much as when they were working. You know, when you're working, you're doing a lot of physical activity, I'm assuming. That keeps you fit. But you retire, you stop doing it. So if you wanted to improve their health, maybe you should, look into that as one of the possibilities. And maybe it's stressful related. Policemen have a higher suicide rate than lots of people. I thankfully don't have the job that they've got. Can you imagine the stress involved in? Most people don't meet policemen in nice situations. Isn't the reason you meet a policeman is because you're in trouble or you're causing trouble? And neither of them tend to be pleasant situations for anyone. So whatever that may be. But we got an interesting result. Evidently, policemen have a worse health rate when they retire than other professions. Let's pick another story. Uh-oh. Yeah. A sample of college students was asked whether they would return money if they found a wallet on the street. I'll call it's one of these honesty questions. The ones that you are probably going to be skeptical about as how truthworthy they are. But nonetheless, we have some data on this particular one, and it was 93 women in their sample. And would you believe how honest they are? 86 out of the 93 said they would return money if they found it. That's the women. Now, of course, self-identified men. They came out, and there were 75 of them. And 51 of that 75 said yes. Would you be skeptical, as I would, on this entire analysis that we're about to do?
Yeah, I feel like this would have been better as an experimental versus an observational.
Yeah, that would be cool. They do that sometimes. I've seen newspapers where they got a wallet and they put $20 in it, and in that wallet they had a telephone number, a card with the guy's name and telephone, and they wanted to see how many people would actually phone the person and say, "I found your wallet," you know, that kind of thing. That was a very interesting article I read. They did that, and they found, as you might expect, a large number of people kept the money. Now that was more of an experiment, because saying what would you do is not quite the same as what you would actually really do if it was in front of you. But they found some very interesting versions of that. They had a wallet with the money in it. I'm saying $20. It could have been $100, whatever it was, right? But they put the money in it, and they had 3 versions of that wallet, right? One of them had the money in it, and that's all, apart from the card. The other had a wallet in it and a picture of the person, right? And the third one had a wallet with the money and the picture of the person with his wife and kids. And do you know that the percentage of returned, i.e., they phoned them up and said, "By the way, I've got your wallet and there's some money in it." Do you know that they weren't the same in each of those 3 categories? The one that only had money was the least. People did, honest, there are honest people out there. They did phone some of them, right, and say, "I've got your wallet." Do you know what the next one was? The one with the picture of the person, just a picture. That increased the rate at which people would phone. And the biggest one is when you had a picture of you with your family. And I think that is reflecting, the more anonymous the crime is, the easier it is to commit. I'm not saying stealing money, well, it's a big crime, but you know what I'm saying. That if you feel connected to that person, even if it's only through a picture, or, "Oh, look at that in his family, how can I steal this guy's money? He probably needs it for the rent or something," right? You're just more likely to be honest. It's an interesting story. On hand, these people, do you know what this tells me, which is not what it's meant to tell me? It tells me men tell the truth more often than women. How on earth have I came up with that as a theory? Yeah, how have I came up with that as a theory? That men tell the truth more often than women. Totally sexist. I think that's more realistic than that. I think more men actually said, "Yeah, I'd keep the money." You notice fewer women said that.
But you don't think that women are more likely to return the wallet?
If that was the case, that would not be a sexist comment, but since I chose mine, it is a sexist comment. I'm assuming that you're both the same. and the returning was a matter of how truthful you are. Right, back to this guy. Want to collect all the good stuff. Let's go for a 99. So it's going to be P1 hat, take away P2 tap, and we'll stick in the magic Z score for 99, which is 2.576. And it's going to be P1 hat and Q1 hat. So I guess I better turn these into decimals. Oh, I just thought I can do this. 86 over 93, that's P hat. The other amount would have been 7. And this one is 51 over 75. And the other amount is 26. And this lot is going to be divided by 93. And this lot is going to be divided by 75. I could actually probably do that in the calculator if I'm really careful about brackets. So I am going to try that and see if I actually get to do it. And if I screw up, which I am likely to do, isn't the moral of that story is turn the damn things into decimals, because it's less likely to screw things up. But here goes. I'm just going to do the margin of error. So it's 2.576 times the square root. Now, as long as I keep enough brackets in here, I should be fine. So the first fraction is 86 out of 93. I'm going to multiply that by 7 out of 93. That's the ones that said they would actually have kept the money. And then divide the whole thing by 93. Then I'm going to add, and I'm putting a bracket around it. And the first guy was 51 of the guys said they would keep the money, would return the money. And they would multiply it by 26 divided by 77. And that should get divided by 75. Now that kind of answer should be around about 2%. Yeah, that's good. I got it. So we have P1 hat, which I'll return now. Get this guy finished. Yes.
Where did the 77 come from? You have 51 over 7.
Oh, shooting space and things that aren't nice. It should have been 75, shouldn't it?
Oh, okay.
I can fix that.
Okay.
I'm just going back into the calculation. I hit center enter. The good news is I think it's such a minor mistake. The answer's not going to be anything real. Yeah, it made no real difference. So it ends up being plus or minus 0.159. It would have been 157 on the previous one. So virtually no difference. So back to this fella. P1 take away P2 is basically going to be 86 93rds. Take away 51 75s. And that answer is 0.245, 3 decimal places. And we should be able to get around it from now. 0.245, take away the margin of error, which is 0.086, and then add the margin of error. And we got 0.404. So somewhere between 8.6 and 40.4%. So if we make the assumption that this was honest data, we have came to the conclusion that the difference between men and women, right, women and men, is this interval. Since it's all positive, this is statistically significant. And since it is all positive, does it not mean the women are bigger than the men? So it's statistically significant that women will return the money more often than the men. True story. Show you how honest my wife is. Do you know you go into supermarkets and you have loads of stuff and you have it in your basket and you put it out, and then there's a little thing that's stuck under the corner and you don't even know it's there, and you know you've paid for your groceries and you go out. This has happened at least twice in our married life. Once we're emptying it into the car, she notices something at the bottom. She said, "Oh, we never paid for that." Without a second thought, my wife always goes back into the supermarket, goes over to the cashier and says, "I need to pay for this." That's how honest my wife is. I'm not saying I wouldn't do that, but I'm so bloody lazy, I probably wouldn't. It's not, yeah, unless it was something really expensive, then I'd feel guilty. I have, so to my own credit, I have found money on a casino floor, and I did take it over to the cashier, the security people. And so I have done my bit, but that's me wondering, as I frequently do. I think what we need to do here is get you lot to do the next one. So I'm going to give you a question, and it's going to be the same guy. This is like our last shot at doing the difference between two groups. And I'm going to give you the data, and it's your job to find the difference in the two. I'm trying to find a medical one if I can. That's a political one. I don't know in that one. Okay, this one is similar to question 11. Fatty acids are present in fish oil, may be useful for treating some psychiatric disorders. Never knew that. An article described a random experiment done by a medical researcher in which 17 bipolar patients received fish oil daily, while another 19 of them just got a placebo, right? So probably a little gel capsule, right? So the data is those who have bipolar disorder, and the sample size was 17, and the percentage success is based on people who felt that their situation had improved in some way, right? So it'd be quite an objective thing. But they came up with the answer that 7 out of 17 of them said that their bipolar issues had subsided a little. And then I guess I should call these the placebo, because they are. Agreed? And in that second group, there are 19 in that group. And those who said that their condition had improved was 2 out of 19. And somewhere in here, we're going to find a 95% confidence interval. Okay, go for it, guys. Last question for today. Find and do the whole analysis. After the interval, I want you to say if it's statistically significant or not. Okay, guys, let's see. You can catch up with me where we are. Okay, so the percentage of the bipolar group received the fish oil, 41% had an improvement and the rest didn't. For the placebo group, about 10% had an improvement, the rest didn't. The standard error of this particular story is going to be 0.412.588 and divided by 17. And the Q2 is 0.105, 0.895 over N2, that's 19. You know what I'm like with buttons, so you can tell me if you got the same number when I'm finished. Now you may have rounded off differently, so take that into account. We might not be exactly the same, but we should be in the same ballpark. And I get, if I round it off to 3, which is kind of going right, I get 139. How does that look? Okay, so I didn't screw up there. So we're going to take the difference between these two. And I guess I should do that right now. So if you take 0.41412 and you subtract the placebo group, which was 105, you get 0.307. Give or take, for a 95, it's 1.96 times the standard error, which is 0.139. So we're going to have 0.307 with a margin of error of 1.96 times 0.139. And I'm looking again to the 3 decimal place mark. Looks like it comes out to about that. Does that look good? 0.272, because it looks kind of big to me. Huh? It is what it is. Of course, it is going to be big. Sample size are tiny. Yeah, it's not a strange thing. Okay, so I got an interval. Let's see what that looks like. 0.307, take away 0.272, and the answer I get is 0.035. And if we go the other side, 0.307, add 0.272. Oh, darn it in space. Should do that in my head anyway. It's 9, it's 7, it's 5. Okay. So we are looking at essentially 3.5 to 57.9%. Now, since this is the last question, I'm going to get quite a few pointers out of this one. First one almost caught me off guard. Isn't the margin of error massive? Plus or minus 27%. But that was caused by tiny sample sizes. Technically speaking, if we're not careful, we will look at that and we will say statistically significant result. Why? Well, all the numbers are positive. Shouldn't that mean that taking fish oil in some way is helping people with bipolar disorder? And the reason why I kind of phrased it in that vacant way is that we shouldn't have done the experiment in the first place, not with that data. And it wasn't because people lied, because I'm pretty sure that they didn't. I don't think that's the main reason. You know, like they said, it made them feel better and it didn't. I don't think that's an issue. What is my issue?
It doesn't fit the rule of 10.
Correct. The rule of 10 doesn't mean the sample size should be 10. The rule of 10 is the people who said yes and the people who said no, right? The P's and the Q's both have to be at least 10. Well, if you look at this, 7 yes, 10 no's, fails. 2 yes, 17 no's, still fails. If even one piece of the puzzle is broke, right? In fact, that's where the analysis should have stopped. I ain't got good enough data to do anything. Can you imagine an unscrupulous person who worked for a fish oil company wanted to get doctors to prescribe fish oil, psychiatric doctors, I'm assuming, right, as a treatment for bipolar disorder? If you're a doctor and you don't understand the rules of statistical significance and when you can and can't, wouldn't that be reasonably convincing to you? Hey, 2% improvement, 3%, okay, that's worth it. Wow, I could get a 50% improvement. It's worth the risk. It might help, this patient Joe that I've got. These do not get published. These kind of things do not get published in reputable journals, because what happens in the process is that you do your experiment and you do your analysis and you publish it and it gets peer reviewed, which means you send it to the Lancet, right? Whatever the journal's going to be. And the Lancet, the publishers, send it to 3 independent people who specialize in that type of field. And they say, look at this data and tell me, is it valid? Is it telling what they say it is? And they're going to look at that and say, what's this guy doing? Look at the size of that sample. It's not even valid to do the experiment. And that paper gets thrown out and it never gets published. And that's the way the medical and scientific world tries to stop. They try to filter out bad conclusions because they've been done statistically poorly. Right? Otherwise, couldn't you just make up your own rules and say, 10 people's enough to ask anything. I'll get a significant result. I'm going to publish it, and well, can you imagine the hassle that would cause in the medical field if everything that you did was allowed to be published just because you thought asking 10 people was enough? Good report, that. That's a good question, not because of the answer, but because of what's wrong with the process. So when you look at somebody trying to prove something to you with this stuff, you start at the beginning. Did they collect the data in an unbiased way, right? So remember response bias. People could lie about whether they give the money back, right? Wouldn't that destroy your conclusion if response bias, right? And couldn't you also get biased by asking people questions in a bad way? Right. Here's an example. Suppose I wanted to get people's opinion on abortion. Really touchy subject, right? Very sensitive to a lot of people. If I went and said to you, are you in favor of killing an unborn child? Do you think that is a very fair way to ask an abortion, your opinion on abortion? Of course not, right? But if you phrase it the other way, you could say, are you in favor of a woman's right to choose to have an abortion? Now, you might think that's a very fair way of asking that question. Do you know, anti-abortionists would think that that was a very biased way of asking that question. The only fair version of that question is, are you in favor of abortion? You don't qualify it with a negative or a positive statement because you influence the answer. And you will. If you're really good at it, you could influence it a lot. Don't ask questions that are people going to lie unless you can figure a better way of getting the truth out of them. Like, I'll give you $100 if you tell me the truth. I don't know. Whatever it is, do that. Make sure your samples are big enough. Fails there. Make sure, if it's at all possible, that you get a simple random sample. In other words, the people that you ask are a fair representation of the population, right? So if I'm interested in who's going to win the next general election, do not go and wait outside the unemployment exchange and only ask people who are going in and out. Right? Don't go to a big fancy hotel and ask people who are going in and out, right? Can you see that you could definitely get biased data because it's not a simple random sample? There are lots of ways you can screw up your experiment. But if you get everything right, the data will be the truth, statistically significant at least. And that's the holy grail of statistics. So whenever you see reports, what you always have in the back of their mind, How could they have screwed this up? Is there something they might not have told me? And that is a good place for us to finish.